Oddly. If the engine is the heart of the ship, then the valves. They are the heart valves. If they don't open and close exactly when they're supposed to, at the exact pressure they're designed for, the whole system just goes into cardiac arrest.
And that's really the mission for this deep dive. We're going to ignore the big flashy pistons today and look at the circulatory system. We want to understand this hidden architecture of the engine room.
And it's not just plumbing.
No.
Yeah.
It turns out choosing a valve is actually a high-stakes game of physics.
It absolutely is. Because you have to remember the environment. You're dealing with fluids that actively want to destroy whatever is containing them. You've got seawater that wants to corrode everything it touches.
Right.
You've got steam at pressures that could slice through bone. You've got heavy fuel oil that wants to catch fire. A valve isn't just an on-off switch. It's a containment device that is literally holding back a disaster.
And the guide makes it so clear. Get the selection wrong, and you don't just get a leak, you get a catastrophe. So let's start where the guide starts, with the most sort of fundamental choice an engineer has to make.
Okay.
Do you want to stop the flow completely, or do you want to control how much is flowing?
This is the isolation versus throttling debate. It sounds simple, but in practice, this is where the most expensive mistakes happen.
So the first character in this story is the gate valve. Now, looking at the schematics, this thing just looks like a medieval portcullis.
That's exactly why it's called a gate valve. The principle is very simple. You have a gate that slides down across the pipe and blocks the flow.
And the big advantage here, it seems, is the lack of obstruction. When that gate is lifted all the way up, the pipe is basically empty.
Right. It offers what we call full bore flow. So if you have a 12-inch pipe and a 12-inch gate valve, when it's open, you have a 12-inch hole. There's almost no friction, no pressure drop.
The fluid just glides through.
Exactly. And that's why we love them for isolation.
Yeah.
If I need to fix a pump, I shut the gate valves on either side and boom, the pump is totally isolated.
And this is where the guide starts practically shouting, in all caps, do not use for throttling. You cannot leave this thing half open.
Never. It is a binary device. It's open or it's shut. There is no middle ground.
Okay, but I'm trying to picture the physics of why, though. I mean, if I open a door halfway, I can walk through it. I just have to turn sideways. Why can't water do that?
Because you aren't water moving at incredibly high pressure. Think about putting your thumb over the end of a garden hose. What happens to the water?
It sprays out way faster. It turns into a jet.
Exactly. It accelerates. Now, scale that up. Imagine that garden hose is a steel pipe, and the water has thousands of pounds of pressure behind it. When you leave a gate valve half open, you create this tiny crescent-shaped opening at the bottom.
Right.
The fluid has to squeeze through there, so it accelerates to, well, almost supersonic speed.
And that creates, what was it called?
A phenomenon called wire drawing.
Wire drawing.
That high-velocity jet acts like a saw. It causes erosion, cavitation. It literally cuts grooves into the metal seat of the valve. It looks like someone took a wire cutter to it.
So you physically ruin the valve.
You ruin the seat, which means the next time you try to close that valve fully, maybe there's a fire or a burst pipe, and you really, really need to isolate that line.
It won't seal.
It won't seal. The water just hisses right through those grooves you created. You've turned your primary safety device into a SIF.
That is a complete nightmare scenario. You think you've shut off the fuel, but you haven't.
Which is why experienced engineers always look for the rising stem.
Ah, I saw that term. That's a physical feature on the valve itself.
It's a visual cheat sheet. On a rising stem gate valve, the mechanism is exposed. When you turn the wheel to open it, the threaded stem literally rises up out of the handle.
So you can see it from across the room.
For sure. If you walk into a noisy engine room where you can't hear yourself think, and you see a stem sticking up 6 inches, you know instantly that valve is open. You don't even have to touch it.
That's brilliant. It communicates the state of the system without needing a screen.
Okay, so gate valves are for stop and go. But engines aren't always binary, right? Sometimes you need a dimmer switch. You need to regulate.
And that's when you bring in the globe valve.
The design here is totally different. The guide describes it as a Z pattern inside.
Right, so in a gate valve, the water goes straight through. In a globe valve, the water has to come in, go up, pass through a horizontal seat, and then go down and out. It's forced to make 2 90-degree turns.
Doesn't that just kill your pressure? I mean, you're forcing the water to do parkour.
It does. It absolutely creates resistance. But in engineering, resistance is control. Because the fluid is already losing energy making those turns, we can move the disc closer to the seat to throttle the flow without creating that destructive wire drawing jet we just talked about.
So the valve is actually designed to take that punishment.
Precisely. So if I'm looking at, say, the steam line heating the fuel, where I need to keep the temperature exactly at 135
You're
degrees.
using a globe valve. You're using a globe valve. You can dial it in. It's the difference between a light switch and a volume knob. You trade a bit of efficiency for a lot of precision.
Okay, so we have the gate for isolation, the globe for regulation, but both of those sound, well, heavy. They're these big cast iron things with wheels that must take forever to turn. What happens when you don't have the space or you just need speed?
Then you enter the world of quarter-turn valves.
Which is where the ball valve comes in. I think most homeowners would probably recognize this one.
Oh, yeah. You've got one under your kitchen sink. It's a ball with a hole drilled through it. Simple as that.
And the guide seems to love these for fuel lines and airlines. Why there?
Speed and seal. To close a large gate valve on a big pipe, you might be standing there turning that hand wheel for, I don't know, 2 minutes, hand over hand, a ball valve.
One motion,
Clack, 90 degrees,
closed.
less than a second. And because it's a machined ball inside a socket, it's practically airtight. Great for compressed air or fuel, where even a tiny leak is a big problem.
But I'm guessing the same warning applies.
And I feel like a broken record here, but yes, do not throttle with it.
Same reason, the wire drawing thing.
Similar physics, just different damage. If you leave a ball valve half open, that high-velocity fluid hits the edge of the hole in the ball. It eats away at the seals, at the metal edge. Eventually, the ball gets pitted, and it won't turn smoothly or seal tight anymore. It's meant to be fully open or fully shut, period.
Now, there is another member of this quarter-turn family that solves a really specific problem, space. The butterfly valve.
The butterfly is the true minimalist of the valve world.
It looks incredibly thin in the diagrams, almost like a wafer.
That's exactly what we call it, a wafer type. Imagine you have a massive pipe, say the main seawater inlet for cooling the engines. That pipe could be 20, 30 inches wide.
A gate valve for that would be the size of a car.
And it would weigh a ton. A butterfly valve is just a disc on a spindle that sits inside the pipe. When it's open, the disc turns sideways, so it's just a thin line in the flow. When it's closed, it turns flat and blocks the pipe.
So it just fits right between the pipe flanges.
Yep, takes up almost no room at all. For systems like the fire main or ballast water, where you're moving huge volumes of water and space is tight, they are perfect. You see them everywhere on modern ships.
Is there a catch? There always seems to be a catch.
The catch is the seal. They aren't as good at sealing against really high-pressure differentials, not compared to a globe valve. And because that disc is always in the middle of the flow, even when it's open, it creates a little bit of turbulence. But for just moving bulk water, it's the industry standard.
Okay, let's move on to precision. We talked about globe valves being the volume knob, but sometimes you need more of a scalpel. The guide mentions the needle valve.
A needle valve is basically a globe valve that went on a diet. It is a long, thin, tapered point-a-needle instead of flat disc.
And the threading on the screw is super fine.
Extremely fine. You might turn the handle 3 full times just to lift the needle a single millimeter.
Why would you ever need that level of, well, annoyance? I mean, who has the time?
You make the time because you need to protect the expensive stuff. Think about a pressure gauge. It's a delicate instrument. It's got a tiny spring mechanism inside. If I just open a ball valve and slap that gauge with 50 bars of pressure instantly, pop. Exactly. You blow the internal Borden tube. The gauge is dead. With a needle valve, you crack it open microscopically. You let the pressure equalize. Hiss, hiss, until it's stable.
So it's like a surge protector for fluids.
That's a great way to put it. It protects the instrumentation that tells you what the engine is actually doing.
Now, everything we've discussed so far needs a human hand, some grease-covered engineer turning a wheel.
That's what you use for those automatic control valves. Hydraulics using oil, that's for pure power. If you have a huge valve on the sea chest that's underwater and takes 5,000 pounds of torque to turn, you aren't doing that by hand. You use hydraulics.
It really is a mix of eras, isn't it? You have these Victorian-era cast iron wheels right next to fiber optic sensors controlling pneumatic actuators.
That's the modern engine room in a nutshell. It's a living museum of mechanical history. You need to know how to program the computer, but you also need to know how to swing a wrench.
So, stepping back from the parts list, we had a
Chance. Automation is the trend.
But the guide also hammered home that gate valves break if you use them for throttling. That relies on a crew member knowing not to do that. It relies on the human understanding the physics of wire drawing.
It relies on training, on experience.
So if ships are becoming more and more automated, are we approaching a future where no human hand ever touches a valve? where that judgment call is just gone.
We might be. But sensors fail. Wires corrode. Computers crash.
And when the computer screen goes black in the middle of the Pacific, you might find yourself really wishing you had a big, heavy iron wheel to grab onto.
And the knowledge of which way to turn it.
Thanks for taking the plunge with us today.
Safe voyage.